Okay. So, continuing with Legendre polynomials. So, what we've seen from last time is that we have the Legendre differential equation that's an eigenvalue problem, and the Legendre polynomials are solutions of that equation, so they are eigenfunctions. And the differential operator for that eigenvalue problem is already shown to be self-adjoint. The coefficients were 1 minus x squared minus 2x, and the second being derivative first. So that automatically ensures that these eigenfunctions, Legendre polynomials, are orthogonal. So we have this relationship, the integral from -1 to 1 of the product of Legendre polynomials is 0 if the Legendre polynomials in question. Did I say Lagrange? I totally said Lagrange. I probably said Lagrange like 5 times. Because I'm dealing with Lagrange polynomials during the previous hour. Okay. Whatever polynomial I mentioned starting with L, I mean Legendre. So let's back up a little bit. I'm surprised they even caught that. Okay, so the integral from -1 to 1 and the product of two distinct Legendre polynomials is 0. The reason why the domain of the integral is -1 to 1 is that x equal plus or minus 1 are singular points of the Legendre ODE. So we cannot count on solutions being defined outside of the integral -1 to 1 because of that singularity. So that gives us our domain. We can certainly ensure a unique solution for each eigenvalue on -1 to 1. That's Legendre polynomial. Okay, so in so many words, way too many words, they're orthogonal. And this is the inner product. Okay. Not my day. So, okay, well, I was fighting Michael Hangel much today. It's largely dissipated, but still, now, when n is equal to m, then we're going to the integral of Legendre polynomial squared. So what is that going to be equal to? We don't know that yet. So for that, we're going to make use of the generating function. So what I do is, this is the generating function for Legendre polynomials squared. Recall it was to the -1/2 power. So I squared that. And because the generating function is going to be equal to this summation here, is power series in t. So I'm going ahead and squaring that. So now what I can do is, if I were to carry out the multiplication of this power series, I have a double summation of like m and n going from 0 to infinity. In fact, I'll just go ahead and write out what that looks like. That would be equal to sum for m and n going from 0 to infinity of p m of x, p n of x, t to the n plus m power. Subscript y. Okay. So suppose I integrate both sides of this equation from -1 to 1. So on the left side, I'm just going to have this. On the right side, when I integrate this from -1 to 1, that means in each term, I'm taking the inner product of Pn with Pn. But as we can see up here, that's going to be 0 when n is not equal to m. So the only terms, when I integrate from -1 to 1, the only terms that are going to survive are the ones where m and n are equal. So I'm going to have t to the 2n, which I can pull outside the integral. And then I'll have these integrals left over. So now I have this power series in t involving only even powers of t. So if I can work out this integral in such a way to also have a power series in even powers of t, I can match coefficients, and then I'll be able to get a handle on what this is. So now that's what I'll do. So to work this integral, I make this u substitution, or I guess we call it y substitution in this case. And when I carry out the substitution, this is a new integral I get. It's a lot easier to work out. I just have natural log of y. So then I go ahead and plug in my limits, 1 plus t squared and 1 minus t squared. And using the properties of the natural log, I get this. But then I can use the Taylor expansions of natural log of 1 plus x, where x is equal to either t or minus t. So now I have power series representations of these two. And we have x to the n in both of these, so I combine into one term. But here I have this minus 1 to be n minus 1, so I've been adding 1. So depending on, so when n is, okay, when n is, be careful about this. Something seems off here. Yeah, something is off. Yeah. That should be t. Okay. I think this wasn't caught 9 years ago. All right. Let me check on the rest of this. All right, and over here I have minus 1 to the n minus 1 and minus 1 to the n. This has minus 1 raised to 2 consecutive powers. This product is going to be equal to minus 1. But then I have a minus, so I get a plus 1 here. So, okay. So when n is even, then I have minus 1 to an odd power, which would be minus 1, plus 1 will be equal to 0. So in other words, when n is even, this becomes 0, so all those terms go away. So the only time I have a non-zero term is when n is odd. So this will end up being a sum from 0 to infinity of t to the 2n plus 1 over 2n plus 1. But then I have to divide by t. I get this 1 over t hanging out here, so I have t to the 2n. When n is odd up here, I'm going to have 2. So that's going to give me a factor of 2 that I can pull outside of the summation. Okay. So I got what I wanted. I have the integral evaluated as a power series involving even powers of t. So what I can do now is the coefficients of this power series, 2 over 2n plus 1, that's what these integrals are equal to. So now I have the results of the scalar product of the Legendre polynomial. Keep watching with them. Legendre, not Lagrange. Legendre polynomial with itself is 2 over 2n plus 1. So I put all the results together. The scalar product of any Legendre polynomial with any other Legendre polynomial is this, where delta mn is the Kronecker delta that's equal to 0 when n is not equal to m, and 1 if they are equal. So, plus aside, questions about anything that happened here, especially with this. at least now those are correct. But okay. Now, the other thing I'm going to present today, is actually something I'm going to start today, but I'll finish next time. Where Legendre polynomials come up in the process of solving a PDE. The PDE in question is a fundamental one. It's Laplace's equation. So Laplacian of u is equal to 0, but in spherical coordinates. That's what complicates matters a lot. So here are the spherical coordinates I'll be using. Okay. Right, and I guess this is based on the more physicsy convention, where we have the angle phi plays a role similar to that of theta from polar coordinates. So here we have our expressions for x, y, and z in spherical coordinates. And then going the other way to express the spherical coordinates in terms of Cartesian coordinates. So I wrote one of these ways of writing these change of variable can come in handy. One thing I want to point out, it's better to write it this way, tangent of phi is y over x, instead of simply saying phi is equal to inverse tangent of y over x. The reason for that is, by convention, inverse tangent can only return an angle between minus pi over 2 and pi over 2. In other words, it ignores the entire left half of the xy plane. It's okay. So if your point xy as x is negative, you'd have to add pi to whatever inverse tangent returns. So that's why it's written this way instead. Okay. So when you carry out this change of variable in the spherical coordinates, then the Laplacian, which is uxx plus uyy plus uzz, ends up becoming this big mess. So this right here is Laplace's equation in spherical coordinates. So now to solve this, we're going to use standard technique for solving PDE, separation of variables. So we assume that our solution u is a product of a function of r times a function of beta times a function of phi. So we substitute this representation of u into the PDE, and then we divide by capital R times capital beta times capital phi. And when we do that, instead of these partial derivatives, we're just taking ordinary derivatives of each of these functions of a single variable. And then this is what we get. Now, this is still quite a mess. But then what we do is, by some rearranging, now we have this. The left side is a function of only phi. The right side is a function of only r and theta. R, theta, and phi are independent variables. The only way that you have this kind of equality across all r, theta, and phi under consideration in your spatial domain is that both of these expressions on the left and right side must be equal to a constant. So I'll take the left side and set that equal to this constant, minus m squared. And so this ODE has this solution, e to the plus or minus im phi. Reason why I use a minus sign here, I could have put any constant here, but since this corresponds to the I'm now going to mangle this word, the azimuthal angle. I think we can see why I don't like words. Okay. The solution must be 2 pi periodic. The only way that can happen is if the constant that we have here is negative. Furthermore, not only must it be negative, it must be that the m has to be an integer. So that's how we get 2 pi periodic solutions. So now, so this left side is equal to a constant. It's minus m squared. So one variable has been taken care of. We know what capital phi is. And that helps us work out what the rest of these are. So now I set this equal to minus m squared and do some rearranging again. Because what it lets me do is it lets me isolate functions of little r on the left side, functions of little theta on the right side. So same situation. Each side depends on a different independent variable. So again, both sides must be equal to a constant. So I'll call that constant lambda. So by setting this equal to lambda and then this also equal to lambda, then these two ODEs pop out. All right. Now, whoops, I've actually already reached into my notes. What happened there? You need to go early, didn't you?
Oh, it's at 7, not 6:30.
Oh, okay. Okay. So, what's going to happen, and this is what is in the next set of notes, is actually not this equation. This equation for theta, we'll be able to make a change a variable in this equation so that the Legendre equation will come out of it. So that we'll be able to express the solution of the theta part in terms of Legendre polynomials. So that's the role that they're going to play in the solution of Laplace's equation on a sphere. I'm wondering, this is going to be something that I would spend a whole class period in, full 35 minutes when I taught this class 9 years ago. Now, granted, what I would have been doing back then is writing all of this on the board, apparently incorrectly in some cases. And now I'm not doing all of that. I'm just focusing on the main things. So that tends to make things go a little faster, maybe too fast in this case. So first I'm going to ask, does anyone have any questions about what we've seen here?
How did you say that word?
Azimuthal? Well, I'm hard to guess which word you're referring to.
Yeah.
Yeah, okay. I'm going to write it in here. All right. Yeah, that.
I thought the M you were saying a B.
B?
Yeah, I thought you were saying B instead of M.
Azimuthal?
Yeah.
Is it named after like a person?
I doubt it. Well, now I got me wondering, this was like maybe some formation times or something. And kind of like studying Pythagorean or something like that. Yeah. So check the etymology on that.
Sounds like Mucinex.
Mucinex?
Yeah.
Etymology. It originates from medieval Arabic al-Samut. That's not how it's spelled in Anglicized, but pronunciation is as-Samut. I'm sure I'm making that pronunciation still. And it it means, quote, the directions. Okay. So no, it's not named after someone.
The word medieval and Arabic right next to each other.
Yeah. Yeah, that's strange. Okay. So, go figure. Oh, there is something I do need to bring up. It's actually something from last time. Okay, so I'm going to, wonder if it'll let me close these notes and open a different set. Once, oh, this one. Don't know if it'll show up on the screen. Oh, it's not. It's weird. This. Oh, I see the problem. Okay, so I can just change which one I'm sharing. Okay, so from last time's notes, I realized I forgot something, and I did my post-processing after class. I put it in. Okay, that's to do with Rodriguez formula for the eigenfunctions of a problem such as this. So what I forgot was this Rodriguez formula does not apply to just any ODE that's of this form. It requires the coefficients p of x, q of x to be these forms. So p of x has to be a quadratic polynomial in x, and then q of x has to be a linear polynomial in x. So only when it's of its form does this Rodriguez formula. Regardless of p and q, you do have this formula for wave function, but for this to be valid, you need p next to q of x to be that. So not quite as broadly useful as I indicated last time. So the strange thing was, when I was preparing my notes for today's class, it turned out that this stuff was in there with this information. Like, oh, I forgot that. All right, so had to pop up that little detail there. Okay. Well, in the oodles of time that we still have, are there any homework questions? Okay, you don't have any. Now, do any of the, how many people do we have here? Oh, okay. Do any of the other 5 people in class one way or another have homework questions? You're supposed to be well done with homework.
One more.
Okay, yeah.
Give him a star.
Now, I do mention that, yeah, I apologize that I haven't been grading lately. I meant to do some last weekend, but I was ill. So it is on a to-do list for this weekend to get caught up. This is where I should apologize to you for falling behind that. Also, thanking you for not dumping too much on me in the meantime. So I will not have to. I think there's a grand total of like 9 or 10 assignments. That's across all assignments. That's the whole pile of what still has to be graded. But when you consider that there are 9 people in the class, everyone has to do like 9 or 10. Wait, I guess now it's 8 or 9 homeworks. Obviously. Yeah, not okay, 9 or 10, but we can do 8. That adds up to that's not terribly many over a whole semester. It's
Like 81 to like 80.
yeah, roughly. So yeah, it's also about almost half grad students, half undergrads. Yeah, so roughly 8 assignments, so only 10 in the pile, not bad. Okay, so I should be able to get caught pretty soon, but I mean, generally people are doing quite well, so actually don't think anyone has to be screwed up like great unless they just happen to be getting stuff in. All right. Okay. I'll go to chat. Oh, the chat is just people saying no questions. So, I guess this is a very short class. So,
Exactly at 6.
all right. Hopefully this doesn't result in an excessively long class later.